We've already talked about one reason why we care about momentum, and that was the idea of impulse, and we can link that to force. But there's another reason why we care about momentum, and that is conservation of momentum. So, if there are no outside forces acting on a system, and that is the key qualification here, then the total momentum of the system is conserved. So, we remember from the energy unit that conserved means that quantity does not change. Okay, so if we have a system of more than one object, okay, and there's no forces on that system other than the forces that the objects exert on each other, then the total momentum of the system is going to be conserved, is going to stay the same. And this is really useful when we look at systems where the objects are colliding together or exploding apart. When the objects start together and move apart from each other. This idea of conservation of momentum is going to help us to analyze those systems. So let's take a look at a quick example of this in action. We have a system here of a blue car and a yellow car, and the blue car eventually collides with the yellow car. So let's look at the momentum before and after. So before the collision, the blue car has a momentum of 2,500 kilogram meters per second, just mass times velocity, and the yellow car has a momentum of 800 kilogram meters per second, giving us a total momentum for our system of 3,300 kilogram meters per second. Now, after the collision, we see that the blue car is going to have a momentum here of 1,500 kilogram meters per second, and the yellow car is going to have a momentum of 1,800 kilogram meters per second. And if we bring those two together, we see that the total momentum of our system is still 3,300 kilogram meters per second. So it does not change. That's the idea of momentum being conserved. Another thing we can think about that kind of links this back to impulse is the blue car had a change in momentum of negative 1,000 kilogram meters per second. The yellow car, on the other hand, had a change in momentum of positive 1,000 kilogram meters per second. So whatever momentum that one object gains is the momentum that the other object loses. And the reason for that is, keeping in mind that momentum is force, or average force, times change in time, we know that these two objects are going to exert equal and opposite forces on each other. And that means that their changes in momentum, because the forces are the same, just opposite signs, and the times are the same, their changes in momentum will also be equal and opposite. So whatever momentum one object gains, the other one loses, and the total momentum of the system stays the same. Equation-wise, our equation for conservation of momentum is very basic, just that the initial momentum of the system, pi, adding up all the momentums of the individual objects, equals the final momentum of the system, pf. And so we're always going to be thinking about, we talked about initial and final, we're always going to be thinking about before and after our collision or explosion, because those are really the two cases when we're going to use conservation of momentum. A few tips here about using conservation of momentum. The first thing, and this obviously is the most important one, is use conservation of momentum when we have a situation where momentum is actually conserved. And that's going to be collisions or explosions with no outside forces. So the only forces that should exist are the forces that are acting between the objects in your system. We're always going to start with that equation here for conservation of momentum, pi equals pf. And much like energy and forces, this is going to be one where you're starting with that base equation and you kind of have to make your own equation from there. You're going to be filling in the momentum of what objects have momentum in your system before and after the collision. Okay, and that's really the key. Negative signs are a big one here. They're always a big one, but they're especially big here. We do need to indicate if velocities are in the opposite direction using a negative sign, because momentum is a vector, and we do need to be aware of the direction of the momentum of an object. Let's go ahead and do a math problem with this. So we have this problem where Alex once saw a red car with a mass of 2,100 kilograms traveling the wrong way down Gay Street until it hit a 2,900 kilogram blue car that was initially at rest. So the velocity of the blue car was initially 0, and we're told the velocity of the red car was initially 5 meters per second. Then we're told that the red car rebounds at a speed of 0.5 meters per second, and we want to figure out the velocity of the blue car after the collision. So now that we have a basic idea of what's going on in this situation, I'm going to set up my conservation of momentum equation. Momentum initial equals momentum final. So I'm going to think about what is momentum before the collision, and I'm going to call the red car object 1 and the blue car object 2. So before the collision, we have the red car. So its mass times its initial velocity. So I'll call that V1 initial. After the collision, we're going to have both objects moving. So we're going to have the mass of object 1 times its final velocity is going to be one component of our final momentum, and then we're going to have the mass of object 2 times its final velocity. Now we can go ahead and plug in the numbers we have here for the masses and the velocities of each object. So we know the mass of the red car is 2100. We know its initial velocity is 5. Its final is going to be negative 0.5. I need to indicate that sign there. And for the blue car, its mass is 2900, and I'm just going to leave that as a variable there, V2F. That's what I'm ultimately solving for. So when I go ahead and do my math here, I find that my final velocity for car 2 is 3.98 meters per second. The next part tells me the collision lasts for 0.4 seconds. We want to find the average force on the red car. So for that, I'm going to think about my change in momentum, which is mass times change in velocity. So the change in momentum of the red car is going to be 2100 times final velocity, negative 0.5, minus initial velocity, which is 5. And so I end up getting a change in momentum here of negative 11,550 kilogram meters per second. Now that I have that, I can go ahead and solve for my average force using the fact that change in momentum is also average force times change in time. So that negative 11,550 is going to be equal to the average force times 0.4 seconds. And so I end up getting an average force here of negative 28,875 newtons. Now the negative sign there, depending on how you set things up, that just really indicates the one direction, and it's based off of what I chose as the signs for my initial and final velocities. If I had said the red cart was initially traveling in the negative direction, I would have gotten a positive force there. So usually we're just going to be concerned with the magnitude, but based off of how I solved it, it's going to end up being negative. Now for the blue car, we're going to do the exact same thing. The change in momentum is mass times change in velocity. So for the blue car, it's going to be 2900 times 3.98 minus 0. And if you used your unrounded numbers, you get a change in momentum here of 11,550 kilogram meters per second. And then we can go ahead and solve for our average force using the fact that change in momentum is average force multiplied by time. So 11,550 equals our average force times 0.4. And so we get an average force here. And again, this is if you used unrounded numbers of 28,875 newtons. Folks, this is not a coincidence at all that these two numbers are the same. And this really comes down to Newton's third law. The objects exert equal and opposite forces on each other. And these two numbers, the changes in momentum, also happen to be the same. And that really comes down to the fact that momentum is conserved, right? The change in momentum of the two objects must be equal and opposite so that the total change in momentum of the system is 0. It stays the same before and after the collision. Just a quick side note, because we saw this in the last problem, we saw applications of both of the important parts of momentum, both impulse and conservation of momentum. So just a quick note about when we're going to use them. Conservation is mainly going to be for collisions or explosions between 2 or even 3 objects. All right. Impulse, on the other hand, is going to allow us to analyze the average force or the force versus time graph when we're talking about a single object.